So let's start off by going through the assignment. Identify some factors that can cause a person's blood pressure to increase. And we talked about how stress, medication, exercise. Oh, there we go. Things like that can cause a person's blood pressure to increase. Explain what is more dangerous if an artery rather than a vein is cut by accident. Artery is higher pressure. So go like out of the neck. Pressure. List the steps in taking a person's blood pressure using a cuff. So you inflate over 120. Deflate till you hear lub, deflate till dub, right? The lub is the ventricle contracting, and the dub is the ventricle relaxing until you can hear that second part of the dub, and then wherever it lubs is your first number, wherever it dubs is your second number. Okay. What is the normal values for blood pressure? 120 over 80. And resting heart rate is 72 beats per minute. Okay. That is all for that. And now let's do sample diploma questions. So the resting heart rate and blood pressure readings. So resting heart rate is right where it needs to be, 72 beats per minute. But 120 over 80 is this is a little bit higher than that. So the resting heart rate is within the average range, but the blood pressure is higher than average. Which of the following graphs represents the relative blood pressures at different points? So it's always highest in your arteries. This one's out, this one's out. Right, and then it just gets lower as you go down, which makes A the correct answer. It doesn't go back up when it goes back to the veins. From the steps above, choose the number of the correct option that is used when measuring blood pressure. So first step, you want to place it on the upper arm. Step 2, you got to get it above 120, so 72 isn't high enough, so we got to get it above 160. And then open the valve until blood starts flowing. The average value is 80. No, we're gonna get the bigger number first. So we're gonna get that 120 first, and then we're gonna get that 80 second. So 1467 is the correct answer. And then we're looking for which way will we put the artificial heart valve, right? So blood's got to flow this way, so that would push it closed. That wouldn't work. Again, it's going this way. That would push it closed. That wouldn't work. This would work, and this would work. So these guys are out. So we want to replace. We want it between the right atrium and the right ventricle. So the right side is this side over here, right? It's opposite, so this would be the right side. 100 girls of the same age participated in a study determining the effect of exercise on blood pressure. 50 girls exercised for 60 minutes a day. The other 50 girls did not exercise. The blood pressure of the participant was taken at the beginning and the end of the month. Which of the following rows identifies the responding variable? So they wanted to see the effect the experiment had on blood pressure, right? Exercise was manipulated, and they want to see how that affected blood pressure. And a control group from the study. So the control group is the girls that did not exercise, so D. Right? They wanted to see how it compared to the girls who did not exercise. Okay, let's do a lesson on blood. So describe the components of blood. So you need to know all these components of blood. There. And their role of transportation, so nutrients, waste gases, hormones, blood clotting, defense against pathogens, and distribution of thermal energy. So the average 70 kilogram person has about 5 liters of blood. 55% of that 5 liters of blood is fluid, and 45% of it is cells. So plasma is a fluid, makes up 55% of your blood. It's yellow. It's the fluid portion of blood where the cells are suspended. And then you have blood cells. So you have red and white blood cells. This is kind of what the white ones, and these are kind of look like what the red ones look like. So the 45% are cells. And then these little tiny guys right here are platelets, and they make up less than 1%. And they're responsible for clotting. So we're going to talk about each of these individually. So we'll talk about red blood cells first. So red blood cells are also called erythrocytes. They make up 99% of blood cells, right? So I said before that 45% of your blood is cells. So they make up 99% of the 44%. So basically, like 44% of your blood is red blood cells, and 1% is white blood cells of that 45%. Okay, so their main function is to transport oxygen. Each red blood cell can transport 4 oxygen molecules. They have a biconcave shape, which allows them to move through blood vessels more easily. We want it to be nice and smooth moving through there. Each red blood cell has a lifespan of 120 days. And when they die, they are absorbed by the liver, and new red blood cells are produced in the bone marrow. So that's where they produce red blood cells, is in that bone marrow, and it's a process called erythropoiesis. So as red blood cells mature, they lose their nucleus, and when they lose their nucleus, they're called enucleated, which gives them extra room for the hemoglobin molecule. So red blood cells don't really need to think, they don't need to know what to do. They're kind of just like a trailer. They just move along, so they don't really need a nucleus because they're a transport part. So hemoglobin gives red blood cells their red color and allows them to carry 70% more blood than a blood cell with no hemoglobin. Sorry, 70 times more oxygen than a blood cell with no hemoglobin. So when oxygen is bound to hemoglobin molecule, it's called oxyhemoglobin, and it gives it that bright red color. The more oxygen you have, the brighter red your blood is going to be. So here's a video on blood and oxygen.
You breathe in about 17,000 times per day. It's a process you rarely think about, but behind the scenes, a huge coordinated effort is playing out. Your vital organs, the gut, brain, bones, lungs, blood, and heart, work together to sustain your life by delivering oxygen to tissues throughout your body. Most of our cells need oxygen because it's one of the key ingredients of aerobic respiration. That's the process that produces a molecule called ATP, which our cells use to power their many incredible functions. But getting oxygen throughout our bodies is a surprisingly difficult task. Gas enters cells by diffusing in from their surroundings, and that only happens efficiently over tiny distances. So, for oxygen to reach the cells within our bodies, it needs a transportation network. This is where our 20 trillion red blood cells come in. Each one contains about 270 million oxygen-binding molecules of hemoglobin, which is what gives blood its scarlet hue. To make these cells, the body uses raw materials that become available from the food we eat. So in some ways, you could say that oxygen's journey through the body really begins in the gut. Here, in an amazing display of mechanical and chemical digestion, food gets broken down into its smallest elements. Like iron, the building block of hemoglobin. Iron is carried through the cardiovascular system to the body's hematopoietic tissue. This tissue is the birthplace of red blood cells, and it can be found enclosed within our bone marrow cavities. The kidneys regulate our levels of red blood cells through the release of erythropoietin, a hormone which causes marrow to increase production. Our bodies churn out roughly 2.5 million red blood cells per second, a number equivalent to the entire population of Paris, so that oxygen that makes it to the lungs will have ample transportation. But before oxygen can even reach the lungs, the brain needs to get involved. The brainstem initiates breathing by sending a message through your nervous system, all the way to muscles of the diaphragm and ribs. This causes them to contract, thus increasing the space inside the rib cage, which allows the lungs to expand. That expansion drops your lungs' internal air pressure, making air rush in. It's tempting to think of our lungs as two big balloons, but they're actually a lot more complicated than that. Here's why. The red blood cells in the vessels within your lungs can only pick up oxygen molecules that are very close to them. If our lungs were shaped like balloons, air that was not in direct contact with the balloon's inner surface couldn't diffuse through. Luckily, our lungs' architecture ensures that very little oxygen is wasted. Their interior is divided into hundreds of millions of miniature balloon-like projections called alveoli that dramatically increase the contact area to somewhere around 100 square meters. The alveolar walls are made of extremely thin, flat cells that are surrounded by capillaries. Together, the alveolar wall and capillaries make a 2-cell thick membrane that brings blood and oxygen close enough for diffusion. These oxygen-enriched cells are then carried from the lungs through the cardiovascular network, a massive collection of blood vessels that reaches every cell in the body. If we laid this system out end to end in a straight line, the vessels would wrap around the Earth several times. Propelling red blood cells through this extensive network requires a pretty powerful pump, and that's where your heart comes in. The human heart pumps an average of about 100,000 times per day, and it's the powerhouse that ultimately gets oxygen where it needs to go, completing the body's team effort. Just think, this entire complex system is built around the delivery of tiny molecules of oxygen. If just one part malfunctioned, so would we. Breathe in. Your gut, brain, bones, lungs, blood, and heart are continuing their incredible act of coordination that keeps you alive. Breathe out.
So white blood cells, or leukocytes, make up about 1% of blood cells, right? So not very much. White blood cells have a nucleus because they have a job to do, right? What they want to do is they want to find things that cause diseases and they want to get rid of it. So they're made in the bone marrow. They last 13 to 20 days. So when a disease-causing organism enters the body, your body produces them, so they produces more white blood cells to combat them. So when killing a foreign invader, they engulf them in a process called macrophage, right? And this is an electron microscope here, so these are our red blood cells, and these guys right here are our white blood cells. You can see that they definitely look different, and they're more spherical. And you need to know about relative sizes. From this picture, you can see that white's a little bit bigger than red. So what I can show you is this. So this gives us a sort of scale to work with. So we're starting out with the size of a person, cat, right? Things that we're familiar with, and we get smaller. So now we're at an apple, a phone, 2 apples, coffee bean ant. So these are things that we can still see. Blue LED light, microchip grain of sand. And now we're sort of getting into the world that we can't see. So this is a microscopic organism, a tardigrade, width of human hair. And now we're at white blood cells. So this is how big a white blood cell is. This is a neuron in your brain. And then this is a red blood cell right here. So you can see that white blood cells are quite a bit bigger than red blood cells. And right, this is how big a bacteria is. So bacteria is smaller than a red blood cell. Viruses are much smaller. And look, there's COVID, there's the coronavirus right there. Yeah. So you can sort of see scale. So white blood cells are bigger than red blood cells. So here's a video on white blood cells.
The white blood cells are an important part of our body's immune system. Neutrophils are a special group of white blood cells that play an extremely important role in protecting the body against infections. Mature neutrophils do not divide. New neutrophils are constantly formed in the bone marrow where they develop and mature. Mature neutrophils are released into the blood where they circulate for 3 to 12 hours and then move to other tissues where they survive only 2 to 3 days. These mature neutrophils can be found in large and small blood vessels, as well as in the tiny capillaries in different tissues. In the bloodstream, neutrophils act as surveillance cells searching for infections. Neutrophils can sense a site of infection because of chemicals that are released by the bacteria. Upon detecting these chemicals, neutrophils slow down and begin to stick to the walls of the blood vessel. They then squeeze between the cells of the blood vessel wall and enter the infected tissue. Here, the neutrophils crawl towards the infection as they continue following the chemical signals. At the site of infection, bacteria are coated with antibodies of the immune system and marked for ingestion. The neutrophil recognizes the marked bacterium, engulfs it into its body, and traps the bacterium in a sac called a phagosome. The neutrophil contains pouches called lysosomes, which are full of digestive enzymes and chemicals that can kill bacteria. The pouches, or lysosomes, then combine with the phagosomes containing the bacteria and release the enzymes and chemicals, resulting in the ultimate death of the bacterium inside the neutrophil. After killing and digesting the bacteria, the neutrophil is spent. Having completed its duty, the neutrophil shrinks in size and breaks up into smaller pieces that can be recognized and eaten by other cells.
So platelets are the other part of our blood. There are about 1 platelet for every 20 red blood cells, which means that there's quite a few platelets, but since they're so small, they make up less than 1% of our blood. Okay, so there's more platelets than white blood cells, but because they're so small, if we're talking about volume, they make up the least amount of volume. Okay? So when you have a cut, there are proteins in your blood to stop the bleeding called fibrinogen. So fibrinogen is sort of in an inactive phase all the time, but there's platelets, and when those platelets rupture, they rupture when they come into contact with a rough surface, which sort of breaks them open and starts a series of chemical reactions. So what they'll do is they'll cause that inactive fibrinogen to become active and make a mesh that traps the red blood cells. So as the blood gets caught, it produces a blood clot. Okay, so here you can see that this is our fibrinogen. So normally it doesn't do anything, but when it combines with the chemicals in the platelets, it sort of makes this mesh. Red blood cells get caught as they leave, and that creates our blood clot, and then it hardens and it becomes a scab. So platelets have to do with clotting. Here's a video about us healing.
The largest organ in your body isn't your liver or your brain, it's your skin, with a surface area of about 20 square feet in adults. Though different areas of the skin have different characteristics, much of this surface performs similar functions, such as sweating, feeling heat and cold, and growing hair. But after a deep cut or wound, the newly healed skin will look different from the surrounding area and may not fully regain all its abilities for a while, or at all. To understand why this happens, we need to look at the structure of the human skin. The top layer, called the epidermis, consists mostly of hardened cells, called keratinocytes, and provides protection. Since its outer layer is constantly being shed and renewed, it's pretty easy to repair. but sometimes a wound penetrates into the dermis, which contains blood vessels and the various glands and nerve endings that enable the skin's many functions. And when that happens, it triggers the 4 overlapping stages of the regenerative process. The first stage, hemostasis, is the skin's response to 2 immediate threats: that you're now losing blood and that the physical barrier of the epidermis has been compromised. As the blood vessels tighten to minimize the bleeding in a process known as vasoconstriction, both threats are averted by forming a blood clot. A special protein known as fibrin forms crosslinks on the top of the skin, preventing blood from flowing out and bacteria or pathogens from getting in. After about 3 hours of this, the skin begins to turn red, signaling the next stage, inflammation. With bleeding under control and the barrier secured, the body sends special cells to fight any pathogens that may have gotten through. Among the most important of these are white blood cells, known as macrophages, which devour bacteria and damaged tissue through a process known as phagocytosis, in addition to producing growth factors to spur healing. And because these tiny soldiers need to travel through the blood to get to the wound site, the previously constricted blood vessels now expand in a process called vasodilation. About 2 to 3 days after the wound, the proliferative stage occurs, when fibroblast cells begin to enter the wound. In the process of collagen deposition, they produce a fibrous protein called collagen in the wound site, forming connective skin tissue to replace the fibrin from before. As epidermal cells divide to reform the outer layer of skin, the dermis contracts to close the wound. Finally, in the 4th stage of remodeling, the wound matures as the newly deposited collagen is rearranged and converted into specific types. Through this process, which can take over a year, the tensile strength of the new skin is improved, and blood vessels and other connections are strengthened. With time, the new tissue can reach from 50 to 80% of some of its original healthy function, depending on the severity of the initial wound and on the function itself. But because the skin does not fully recover, scarring continues to be a major clinical issue for doctors around the world. And even though researchers have made significant strides in understanding the healing process, many fundamental mysteries remain unresolved. For instance, do fibroblast cells arrive from the blood vessels or from skin tissue adjacent to the wound? And why do some other mammals, such as deer, heal their wounds much more efficiently and completely than humans? By finding the answers to these questions and others, we may one day be able to heal ourselves so well that scars will be just a memory.
So plasma is the biggest part of our blood. You can see it up in the picture there. It's yellowish in color. It's mostly made of water. It's got suspended or dissolved substances. It transports and holds those blood cells, dissolved waste, urea, hormones, digested nutrients, proteins like fibrinogen, heat. And if you got in a bad accident and you needed fluids, they would use plasma instead of water because it can help replenish those fluids much better than water or a saline solution can. So other parts of our blood that shouldn't be there, other things in our blood vessels that shouldn't be there include cholesterol. So cholesterol is a fat-like waxy substance present in the cell membrane of every blood cell and in food from animal sources. So it's actually important because it's in the cell membrane of all of our cells. So we need cholesterol. Cholesterol is vital to all cell membranes and key to producing vitamin D and some hormone production. But the problem is we get too much cholesterol. And when there's too much cholesterol, the walls of the arteries are used to store their deposits. And what you get is you get a buildup of plaque. So this is a healthy blood vessel. And this one has too much cholesterol. And this is a buildup of plaque in our artery, and it can block that blood vessel. So there's 2 different types of cholesterol. There's LDLs, low-density lipoproteins. So this carries blood protein that carries cholesterol in the bloodstream from liver to rest of body. The HDLs, the high-density lipoproteins, blood protein that carries cholesterol in bloodstream from body to liver cells. So too much LDL is deposits in the arteries and is bad cholesterol. Too much HDL, less likely to deposit in arteries, so we call it good cholesterol. So there's different problems that can happen if you have too much cholesterol. Atherosclerosis is a hardening of arteries due to accumulation of fatty deposits like cholesterol. Fatty buildup leads to loss in elasticity of the heart, which causes stiffness and can occur in any major artery, bodies. Can occur in any major artery bodies. I don't think that's right. Any major artery in the body, maybe that'd be better. And coronary heart disease, so disease in which blood flow through the coronary arteries is restricted, resulting in possible chest pain or a heart attack, right? So if you have, if I go back, this blockage in your coronary arteries, that's when it's really dangerous. That's when you're going to have a heart attack because your heart doesn't get blood and oxygen and nutrients. Angina is chest pain caused by narrowing of blood vessels, so you usually get angina before you have a heart attack. So this is a plaque, this is normal and this is bad. And then if this happens in the coronary arteries, it can lead to a heart attack. So if a plaqued artery becomes rough or cracked, platelets can rupture and release chemicals to start the clotting process. So that's bad. So clots when you have a cut are good. Clots inside of your body are bad. So this rough surface here can cause those platelets to rupture. So this clot can block the blood flow in the artery, and if this happens in coronary arteries, it can cause an instant heart attack and your heart cells start to die. If this happens in the brain, it can cause a stroke. So not good. So here is a video on heart attacks. We will watch that.
Approximately 7 million people around the world die from heart attacks every year. And cardiovascular disease, which causes heart attacks and other problems like strokes, is the world's leading killer. So what causes a heart attack? Like all muscles, the heart needs oxygen, and during a heart attack, it can't get enough. Fatty deposits, or plaques, develop on the walls of our coronary arteries. Those are the vessels that supply oxygenated blood to the heart. These plaques grow as we age, sometimes getting chunky, hardened, or inflamed. Eventually, the plaques can turn into blockages. If one of the plaques ruptures or cracks, a blood clot will form around it in minutes, and a partially closed artery can become completely blocked. Blood flow is cut off to the cardiac muscle, and the oxygen-starved cells start to die within several minutes. This is a myocardial infarction, or heart attack. Things can rapidly deteriorate in the absence of treatment. The injured muscle may not be able to pump blood as well, and its rhythm might be thrown off. In the worst-case scenario, a heart attack can cause sudden death. And how do you know that someone is having a heart attack? The most common symptom is chest pain caused by the oxygen-deprived heart muscle. Patients describe it as crushing or vice-like. It can radiate to the left arm, jaw, back, or abdomen. But it's not always as sudden and dramatic as it is in the movies. Some people experience nausea or shortness of breath. Symptoms may be less prominent in women and the elderly. For them, weakness and tiredness may be the main signal. And surprisingly, in many people, especially those with diabetes, which affects the nerves that carry pain, a heart attack may be silent. If you think that someone might be having a heart attack, the most important thing is to respond quickly. If you have access to emergency medical services, call them. They're the fastest way to get to a hospital. Taking aspirin, which thins the blood, and nitroglycerin, which opens up the artery, can help keep the heart attack from getting worse. In the emergency room, doctors can diagnose a heart attack. They commonly use an electrocardiogram to measure the heart's electrical activity, and a blood test to assess heart muscle damage. The patient is then taken to a high-tech cardiac suite, where tests are done to locate the blockages. Cardiologists can reopen the blocked artery by inflating it with a balloon in a procedure called an angioplasty. Frequently, they also insert a metal or polymer stent that will hold the artery open. More extensive blockages might require coronary artery bypass surgery. Using a piece of vein or artery from another part of the body, heart surgeons can reroute blood flow around the blockage. These procedures reestablish circulation to the cardiac muscle, restoring heart function. Heart attack treatment is advancing, but prevention is vital. Genetics and lifestyle factors both affect your risk, and the good news is that you can change your lifestyle. Exercise, a healthy diet, and weight loss all lower the risk of heart attacks, whether you've had one before or not. Doctors recommend exercising a few times a week, doing both aerobic activity and strength training. A heart-healthy diet is low in sugar and saturated fats, which are both linked to heart disease. So what should you eat? Lots of fiber from vegetables, chicken and fish instead of red meat, whole grains, and nuts like walnuts and almonds all seem to be beneficial. A good diet and exercise plan can also keep your weight in a healthy range, which will lower your heart attack risk as well. And of course, medications can also help prevent heart attacks. Doctors often prescribe low-dose aspirin, for example, particularly for patients who've already had a heart attack and for those known to be at high risk. And drugs that help manage risk factors, like high blood pressure, cholesterol, and diabetes, will make heart attacks less likely too. Heart attacks may be common, but they don't have to be inevitable. A healthy diet, avoiding tobacco use, staying fit, and enjoying plenty of sleep and lots of laughter all go a long way in making sure your body's most important muscle keeps on beating.
So lots of this stuff can seem scary, and you're like, oh no, what's going to happen? How do I got to change my diet, I got to change everything, and no, that's not true. So people make approximately 75% of the cholesterol in their blood from the liver, and only 25% is taken into food, which means that eating foods with lower cholesterol may not actually do anything at all. Okay, it has to do with fats in our diet. You want to have the right type of fats. So here is a chart that shows the type of fats that you want. So these are fats that you want, monosaturated and polysaturated. So these are things that you can eat that are good. And then they will lower LDL, which is bad, and raise HDL, which is good. And this will raise LDL, which is bad. So eating these things is bad. But honestly, mostly it has to do with genetics. And you'll probably be fine because you're young. Okay, that is it. So if you have any questions, let me know.